Hi, everyone. Today we'll be talking about comparing proportions and odds. So Buchi was supposed to take this class, but he's unfortunately unable to be here today. So I'm stepping in his stead. Can you all see my screen? I don't think so.
Yes, I can see your screen.
Can you see the slide on the screen?
It says comparing. It's the banner slide.
Okay, excellent. All right. So let's keep going. All right. So today, a brief outline of. Go ahead.
Yes.
Yeah.
So on the chat, we can't see it. It doesn't seem the chat is open to everybody. It just says hosts and panelists, and then.
No, I think that's on your end. You have
That's
to.
on my end. Okay.
Yeah, you have to just switch where it says everyone.
Oh no, it doesn't give that option. Is my point, and I'm wondering whether other people also have that problem.
Maybe okay. Let's see. Let's allow somebody else to talk.
Mm-hmm.
So first of all, I'm going to make you the host, and then you can just allow an attendee to talk, and because we're not using any new setting, it's the same old setting we've been using.
Okay, my apologies. I think
I see people in Q&A, but I don't see anybody in chat.
Okay. So someone says chat is disabled, so that might be that. So it might be the issue.
Okay. Let's use Q&A. I'm not sure why the chat is disabled.
Okay.
And I don't think that we want to spend time trying to fix that. Okay. If people have questions, let's use Q&A. Okay.
Okay, good.
All right. Yeah. Okay. All right. So yeah, I don't know why the chat is doing that today. So let's use Q&A, please. All right. So this is a brief outline of the proposed set of topics that we will go through. Z-test to compare proportions, it's 2x2 table very quickly, chi-square tests, odds ratios, and logistic regression. So it's a very packed discussion that we have planned for today. And I will jump right in. We're starting a little behind schedule. So, but to sort of tee up the discussion, to prepare us for what's to come, I wanted to just revise the definitions of proportions and odds, as well as odds ratios very quickly. Many of you might have seen this before if you took the EPI 101 class that we taught in March. But if you have not seen this before, this will also be an introduction. So basically, proportions are fractions. So if you have a disease that occurs among 1,000 people, so you have a community of 1,000 people, and you have a disease that occurs among 200 of them, then that proportion will be 200 over 1,000, which is 20%. So essentially, the proportion is the occurrence divided by the whole, okay? The occurrence divided by the whole, that's the proportion. And so, we can then use the proportion to calculate the probability. The proportion is also the probability, but we can also use the proportion to obtain the odds. And this is the key reason why I wanted to show this slide, to sort of set the stage for you to understand that there is a link between proportions and odds. And some of the methods that we use to compare proportions are actually based on the odds framework, and we'll talk about those in a moment, okay? So the proportion is essentially the probability that something occurs, right? The odds, on the other hand, is the probability that it occurs divided by the probability that it does not occur. So occurrence divided by non-occurrence, that's the odds. And we often use the odds in the most common in everyday parlance is in the context of gambling, right? but we also use it in research to engage with proportions in a way that's more risk-based, so to speak, you know. So the other thing that we do with proportions and odds is that we calculate ratios of them, right? So we're able to see whether the ratio of we're able to see whether the ratio of the odds, sorry, we're able to see whether the odds in the exposed divided by the odds in the unexposed, the ratio of both, and our ability to compare those odds is useful. And our ability to compare those odds is useful to help us understand the extent to which the disease might be causing the outcome of interest. Okay, so I'm hoping that this is all introduction and I don't have to like go into too much detail. Okay. So one of the other things that we'll talk about today is a 2x2 table. Essentially, you're able to set up the occurrence and the non-occurrence of a disease using a 2x2 table. And you know, we can draw a 2x2 table like this, where the number of people who have the disease and those who do not have the disease, and those who are exposed and those who are not exposed. You know, you can key in the numbers. If you have 50 people who have the disease among the exposed, you know, 400 people who do not have the disease among the exposed, you can essentially fill up this table and then use that to calculate the odds ratio like this, or the cumulative incidence ratio, which is also the risk ratio. Okay, I'm just mentioning all of this so that you're able to, you know, just get ready for what's to come. One moment, I want to just switch this thing.
Do you need any help from me?
No, so I have two screens and I realize that I'm essentially looking at the screen without the camera. So I feel like I am looking at I'm not looking at the screen where people are. So,
okay.
Or where people will be seeing me, and essentially people will be looking at my side view. So I'm trying to fix that. All right, so can you see my screen now, Ibua?
Yes, I can.
Excellent, thank you. So let's jump into z-tests. So for the last several weeks, we've been talking about a number of methods that, first of all, allow us to describe the population. And then we looked at methods that allow us to compare means, okay? And we said that comparing the means is really a way to compare the distribution of, you know, two variables. And we looked at multiple different methods. We looked at the t-tests, different types of t-tests. We looked at ANOVA, and then we looked at linear regression. And we said that the key thing to always remember is that when we're comparing means, that's in the context of continuous variables. But if you have categorical variables, the way that we usually summarize categorical variables is with proportions. And binary variables or dichotomous variables are an example of categorical variables. We already know that. So if we wanted to compare two binary variables, or we wanted to compare two binary variables, we have to do it using proportions. And one of the more important tests that we use to compare proportions are z-tests. And so we'll talk about z-tests in a moment. But to be able to understand whether the z-test makes sense in the first place, we have to understand like why are we able to use this z-test. Now, let me back up and say that I don't know if it was mentioned, I don't recall if it was mentioned, but in the context of t-tests, when we have a continuous variable, right, we compare the two variables using t-tests, okay? But if the sample size of the two variables are large, say 300, 400, large sample sizes, we could use the t-tests, but at some point when the sample size becomes large, the t-test becomes approximate to the z-test. And so sometimes you will see that z-tests are used to compare continuous variables, right? But the key reason why we're able to do that is because of the central limit theorem. The central limit theorem says that when the sample size becomes large, then the distribution approximates a normal distribution, and then that allows us to use tests that depend on the normal distribution. Now, in the context of a proportion, if you imagine that you have a coin, right? A coin will have two sides, and you have the head and the tail. Now, if you have the head and the tail of the coin, right? If you throw it up, it's either going to be head or tail. That's assuming that you have a fair coin where maybe the edges are not scratched, and every time there is a half chance, there's the probability that you get heads or tail, is 50%. Now, if you do that many times, sometimes you get heads, sometimes you will not get heads, right? And if you do that like maybe up to 10 times, this is what and then you plot, and you plot the probability each time in a histogram, you will get a plot that looks like this. And this is for when the coin is fair, the probability is 0.5. But the key point I'm trying to point out here is that as the number of experiments, number of trials that you're doing becomes large, right, you begin to get something that looks like a normal distribution. We've seen this before many times. This is how a normal distribution looks. Okay. If it's not a fair coin, like in the plot on the right, where the probability is 0.71, for instance, you might not quickly get the normal distribution, but you will eventually as the sample size becomes large, right? So with the fair coin, you're getting to the normal distribution much earlier. But with the unfair coin, you still get to the normal distribution. Initially it's skewed, but it soon becomes normally distributed as well. But that normal distribution that happens, it allows us to use the z-test to assess these variables as well, to compare the proportions for one variable versus the proportions for the next. Do we have any questions at this point? If you have any questions at this point, please put them in the chat, and then we'll take them. But the other thing that we will do as we go along is maybe call people up to, ask questions or to answer questions that we might have. Okay, so the reason why I'm just saying this is to just give you a background for why it's possible to use the z-test. Okay, now let's go to the z-test itself. Okay, now the z-test is basically a test that compares one proportion to another, but in the context of, so we have one raised hand. Haruna, you have a question?
I have a question.
Yes, please go ahead.
Yeah, you say there is fair and fair coin. What's the difference between those two terms?
Okay, so the fair coin, like it's basically, the fair coin is the coin that we all know, that that we all should know, right? If you have a coin where all the sides are round, and each time you throw it up, the chance of getting heads or tail is the same, right? But if you think about the fact that if you have a coin that's maybe the manufacturers didn't create the coin properly, and then the edges of the coin are scratched and jagged, and then it sort of always favors one side. It might be that you're more likely to get heads every time you throw the coin up. So that means that if you think about it, maybe you're in a football match and you need to like choose which side gets to play first, right? So if you have a coin that's not fair, that means that one side is always more likely, the side that chooses the heads, for instance, is always more likely to be the ones to play first. That's sort of the context to understand it. But the reason why we talk about this coin is because it allows us to essentially examine what the probability will be each time you throw the coin up. So for the fair coin is always 0.5, but for the unfair coin, it might be something else. It might be 0.1, might be 0.2, might be 0.7, like we see in this case, right? But if the coin is fair, then you will have a normal distribution very quickly. But if the coin is not fair, and you keep repeating many times, repeat the experiment many times, it will take a while before you have the normal distribution, but you will eventually. I hope that helps. All right, so let's keep going. So if you remember again, we talked about the one sample proportion and the two sample proportion. Sorry, we talked about the one sample t-test, right? In the case where you're comparing a t-test, we're comparing one mean to a pre-specified mean. So we had that context in the first in the last unit where we're talking about comparing means. And that's essentially what's happening here as well in the z-test. You have a mean that you have already specified, which is the p, right? And then you have a p hat, which is the mean, the proportion. You have the proportion that you're specifying, and then you have the proportion that that you're estimating from your data, which is the p hat. And you can use this formula to calculate the z-score, right? And then you can use that z-score in a table. You remember all the statistical tables that we used to have in like 4-figure table in secondary school, essentially the same thing. So you can use that z-score and check the p-values in the z-score, right? And then you will get it. So you obtain the p-value from that, but you can also calculate a two-sided 95% confidence interval in this case. Let me explain this again. For the t-test, we said that it's possible where you have a mean, and we said that mean can be pre-specified, maybe because it's the reference mean, or maybe because it's the reference mean, or maybe because it's a mean that you've obtained from another population that you want to compare to the mean in your own population. In this context as well, you can have a proportion, and let me take an example to make it more concrete. Let's say, what percentage of people in the Stats 101 class understand how to implement linear regression? Okay, so you might say that maybe it's 50% of the class understand how to implement linear regression in R. But if you compare to everybody else, say everybody else who has ever taken a Stats 101 class, you might find that that proportion in that reference population is more like 30%. Okay, so you have a reference population that you've calculated the proportion of, and then you want to compare it to your own proportion in the sample that you're interested in. Okay, so you have a one sample proportion you're comparing to a reference population. Okay, so in that case, you can use this formula to obtain the z-score. So you have a p hat, which is the estimated proportion from your sample, and then you have the p, which is the proportion from the population that you're interested in. So an n is the number of trials. So you can just imagine that you can use this formula to obtain a z-score that you read off in the 4-figure table. Haruna, do you have another question?
I don't have a question.
Okay, all right, thank you. So let's take an example. If you have questions at this point, we can take them. This is a natural place to stop, and if you have questions, we'll take them before we keep going. All right, so I'm going to keep going. So in this example, there's 56% of 45 neonates with intestinal obstruction who were operated at your center that died within 30 days post-op. You're a pediatric surgeon, and you're trying to improve your practice. right? And you're comparing your practice to another practice where they are saying that only 30% of neonates in their own hospital, died for the same condition, the same surgery and everything. So you're wondering, what are you doing wrong? You have 56% to 30%. And the first question you want to ask yourself is this difference statistically significant? That's the context in which you want to use a z-test, okay? Is this difference statistically significant? So you plug the numbers into this formula. You have p hat minus p, and like I said, you remember I said that 0.56 is the p hat, which is what you estimate. Every time you see a hat on top of a parameter notation like this, it's usually the estimate, okay? That means there's one that comes from your sample and the one that you're not sure of. So you're assuming that it's sort of potentially measured with error, okay? So if you plug the numbers into this formula, you obtain 3.806. And you have a two-sided p-value of 0.0001. First of all, who can help us interpret this finding, this p-value? Any takers? So I'm going to allow Ganiat.
Thank you. The p-value here indicates that this is statistically significant.
Yes, correct. This is statistically significant. And before you go, so what inference do you make from this statistically significant p-value?
It means that the 56% of the 45 neonates that died in my center,
yeah,
is significant. It's not the same as in the other center where 30% of neonates died due to the same operation.
Exactly. It's not the same. It's significantly different. And so because it's different, you can then think about it and say, oh, 56 is so much more than 30%. What are we doing wrong? And then you can use that to then take decisions about, or study more the situation in your center versus other centers. Maybe it's infections that's killing the patients. Maybe it's hemorrhage, so you then go and explore that in more detail, and then you take it forward. But the other thing that you can do in this case is that you can also calculate the 95% confidence interval, right? And this is the formula that I use to calculate the 95% confidence interval, okay? So in this case, if you just plug the numbers in, I'm going to call another person who is going to tell us what they think about this confidence interval, 0.415 to 0.705. This is the 95% confidence interval for the difference. Anyone want to tell us how to interpret this? Okay, Otsunaya.
The confidence interval 0.415 to 0.705, if we convert it to percentage, that should give us 41.5% and 7.5%, which does not contain the 30% that we're given in the question. That means it is totally different.
Which does not contain the 30%. Very good. Yes, exactly. So it tells us that, this is statistically significant. So if you were comparing this to, you could either interpret the 0.001, or you could interpret the confidence interval, and you could make an inference based on that. All right, so let's keep going. Now, for the two sample proportion is essentially, instead of bringing the proportion from somewhere else, okay, you bring the proportion from your own sample. Say you have two samples. An example might be you have a randomized control trial, all right? And, you have a randomized control trial. And so one group gets the treatment, one group gets the placebo. So one group, if you check the proportions in one group that gets the treatment, that's P1. The group that doesn't get the treatment, that's P2. You can plug the numbers into this formula, and you also get a Z score that you can check in the statistical table. One point that I wanted to make earlier is that those statistical tables, you can also find them online. Okay, and this is a link at the bottom of the page that can take you to, a page where you can essentially you can essentially, input the numbers that you have, maybe the Z score that you have, and you can obtain a p-value from that. So if you do the same thing here, 6.952, and you put it in that table, you get a p-value. You get this p-value. All right. So this p-value again is statistically significant. I will not ask someone to interpret it, and we can keep going forward. All right. So here you have a drug to treat MS, and 33%, had the disability in the treatment arm. 39% had disability in the placebo arm. Was the drug more efficacious? Right. So because you have a p-value that's significant, you can say that yes, this drug was likely more efficacious than the other one. All right. So I'm going to take questions before we keep going. Any questions at this point?
So there's a question from Emmanuel Ajibola, and he's asking that, does it mean the formula does not factor in the number of neonates studied in the National Center of Excellence? And yeah.
This one. Yes, excellent question. It does not factor in the number. It only factors in the number from the, from your center of interest, from the sample that you're studying. So it's not perfect. I mean, you can get the sense that, oh, maybe this is not perfect, right? But sometimes you don't have that data. You might not know how many neonates were studied at that National Center of Excellence. You might not just have that data. You can't compare. If you had the data, however, then you will have to ask yourself, should I be using this formula, right? And that's one of the things. I mean, if you had the data, you might use the 2 sample proportion, which is here, but there will be some things to think about, and we'll talk about that in a moment. So there are some reasons where some criteria that you have to fulfill before you should go about using the Z-test at all. So I'm sort of teaching it in the roundabout way. First of all, teaching you the mechanics of the tests, and then telling you when you should or should not use it. Okay. All right. So when should you use a Z-test? The first criteria is that, you're interested in proportions, and you're interested in proportions, not just proportions per se, but you're interested in proportions. You want to know how much more different they are, right? So if you're testing, say if you take the example of the surgery that we were talking about earlier, you want to see whether the difference is so much larger. So that gives you an idea of, okay, maybe this is the context where you use a Z-test. And you wouldn't want to use a Z-test in settings where you're looking at natural phenomena, right? Say maybe you're comparing males and females with maybe males and females are your exposure, and you want to look at, maybe we talked about residency hours, for instance, right? So that's one setting where you might not want to use a Z-test. And the reason for that is because if you think that the groups you're comparing are not independent, right? Because first of all, if there's some degree of clustering, that means that knowing something about one group might tell you something about the other group, right? Then that will not be a good setting for a Z-test. You also don't want to use a Z-test if you think that there's confounding, right? If you already think that there's confounding in your analysis, then a Z-test will not be the appropriate test to use. Any other questions?
Sorry, sir, I have a question, sir.
Okay, please ask.
On the example 2 page, in the denominator, we have 0.35.
Yeah, that's an error.
I don't know. Oh, okay.
It should be 0.33. So it's basically from copying from one place to the next. That should be 0.33. Thanks for catching that.
Okay.
Okay.
So there's a question from Victor. And
Okay.
it says, which of the proportions should we use in interpreting the p-value or the 95% confidence interval?
This is in this question. So you're comparing this 95% confidence interval to see whether this 30% is contained in it. So in this case, we can see that this is 0.30, right? It's not included in this range. If this was like a number line, then 30% would be somewhere in front, ahead here, right? So it's a 30% that's the reference you're comparing to the confidence interval to see if it is contained or not. I hope that helps.
I'm
Okay.
sorry, sir. About this example too. I don't
Okay.
know. That denominator should be 0.33. Why are we choosing that and not 0.39? The formula is not indicating maybe P1 or P2. So
you said?
the denominator is not indicating either P1 or P2. So it's kind of confusing.
Right. So if you remember in this case as well, in this one, we didn't use P1 or P2.
Yes, sir. Yes.
We use a reference P here as well. So we're always comparing to a reference. So you're assuming that one is a reference, and then you're comparing the second one to it. But in this case, you're also factoring the n. So it's only the n that's really different in this formula from the other formula, because now you have the information of the sample size.
Okay. If we are using the reference, then for example,
right. So then the p hat. Sorry, I made a mistake. So this p hat, okay, this p hat is the overall proportion in both samples.
Okay. Is there an
right?
addition or?
So it's basically an average. So if you imagine that this is a clinical trial, okay, you have 1,000 patients and you divide them into 500 and 500, and maybe 30% of everybody experience the outcome. Okay, that 30% will be p hat. That's not a sample that that's not an estimate that you have to rack your head too much. You always know, right? But you then look within 500 and 500, maybe in one group, it is 300 people who have the outcome. And that will be P hat 1 will be 0.6 because 300 over 500 is 0.6. And then maybe in the second group, then the P hat 2 might be maybe 0.1 or something like that. Okay. So this is the average of both proportions. I hope that's clear.
All right.
Okay. So yeah, so I made a mistake when I said that this 0.35 was a typo. It's actually the 0.35 is the average proportion in both groups. Okay.
Sorry, sir. Still a bit confused because if I calculate just the average of 0.33 and 0.39.
Yeah.
0.36.
You just get 0.36 something, yeah. So yeah, so but it should be 0.36. It should be the average of both. Okay. Yeah. Any more questions? I think Habib wants to ask a question.
Hello, can you hear me?
Yes, we can hear you okay. We can hear you okay. Please go ahead.
So I can read the question if Habib is having some.
Please go ahead, yeah.
So he says, is it not the 56% that we want to check whether it's significant? That's in the previous example.
In this one.
Hear me?
Okay.
Sorry. Hello, can you hear me?
We can hear you. We can hear you okay.
Okay, sorry.
I think if you type the question
is,
already.
with respect,
yeah.
Sorry, is with respect to the previous example when you were comparing the 56% of the neonates to the 30% in the other center. Is it the 56% that we want to check its significance or the 30%?
It is the 56% that we want. So I think the question that you're asking is the reason why it's not the question that I want to answer, so to speak. Let me explain that. So it's the 56% that we have in one sample. We want to see whether the 56% is related to the 30%. So we're interested in both, right? So if this number was not 30%, this P was not 30% and was maybe 10%, this Z-score will be different and the P value might be different. Okay, so it's not as if we're always only interested in the 56. The reference value also matters. Okay, so when we obtain the confidence interval like this, we want to see whether the reference value is contained inside the confidence interval.
Okay.
Yeah.
All right, I get it now. I was thinking that since it's the significance of the 56% we want to check, I thought it's the 56 that we should check.
Right.
Well, I get it now.
Excellent.
Thank you.
Okay. All right.
Do you have time for more questions or do you want to move on?
I want to move on, yeah.
Okay.
Let's take more questions later. So these are the reasons why you should use the Z-test. You know, when the proportions differ from one another and when the two groups are independent, so just in randomized control trials. So let's move to chi-square tests. Okay. So I'm hoping that we will finish, you know, go a little distance with chi-square test before we take a break and then come back. All right, we talked about the 2x2 table earlier, and so I will not go into much detail, but just to remind you that with the 2x2 table, you essentially are able to look at the number of people in your study and divide them into 4 groups based on whether they have the disease and they're exposed, whether they have the disease and they are not exposed, whether they don't have the disease and they're exposed, and whether they don't have the disease and they are not exposed. So if you have 4 groups like this, you can calculate each of this. And the reason why this is important, you see in a moment, is because these numbers then factor into the calculation for the chi-square. Okay. All right. So the chi-square test. So the other thing that I wanted to quickly say is that if you look at the 2x2 table, here we have the disease up at the top. So it's row, this is the column. The disease is presented column-wise, while the exposure is presented row-wise. It's always important to check the 2x2 table and make sure, especially in the context of chi-square, and make sure that it is being presented in a way that allows you to plug in the formulas correctly. Okay, so here, for instance, you know, in the previous one, we used A, B, C, D. But in chi-square context, you might use something else. D1, which shows disease and exposed. D0, disease and not exposed. H1, healthy and exposed. H0, healthy and unexposed. And this is N1, N0.